Okay. So am I audible and is the screen visible? Can someone confirm? Okay. So okay. Okay. Thanks. Yeah. So hello everyone. Welcome to the course on design and analysis of algorithms. Okay. Somebody has a question. I saw a hand raised. Does anybody have a question? Okay. So, yeah, so let me start by introducing myself. So, my name is Neha, and I'm a PhD scholar at IIT Madras. So, I work in algorithms and circuit complexity and stuff. So, I'll be your. Okay, somebody's microphone is on. Can you turn it off? Unless you want to speak. I think we need Singh. If you can hear me, can you turn off the microphone? Okay, thanks. Okay, so yeah, so I'll be the TA for this course, and what we'll do is this is an 8-week course, and what we will do is we will have tutorials every Fridays, 6 p.m. to 8 p.m. Yeah, and what will typically happen is based on the material covered in the class, we will have some practice questions that will help you solve the assignments. Also, if you have any doubts regarding the previous assignments, you can always ask those in these sessions. And if there is any specific request or specific topic or questions that you would want me to cover, you can you can let me know either in this tutorials, or you can write to me on this email ID. Okay, so yeah. um, okay, so that's the logistics of the tutorials. And these tutorials will try to keep it very interactive, so if you have any questions at any point of time, you can always, you just feel free to ask. mm, okay. I'll, okay, so just to give you a brief overview of what this course is all about, um, what will happen is you will learn some techniques to solve. So you might be familiar with some coding, and given a problem, you try to come up with a code that solves it, or an algorithm or something. So what this course will teach you is some interesting techniques on coming up with algorithms. So particularly you will see greedy. Uh, yeah, you'll see something called greedy approach. You'll also see some dynamic programming. And even if these things don't make sense right now, it's fine. I'm just giving an overview of what's going to happen. So you'll learn these techniques, you'll see how to come up with algorithms. And the nice thing about the course is, if I give you a problem, what you generally do is you try to come up with an algorithm. But what if it's not possible at all to come up with the algorithm? Then how do you convince me that it's not possible? Because you may say that it's not possible, but I would say that I don't believe you. So what we need is some sort of a guarantee, some sort of a proof, or a something solid to make me believe that it's not possible. So what you will look at is some kinds of impossibilities. So this is all the P and P world, and all sorts of interesting stuff. So I'll not get into the details of it, but I just want to tell you what the course is all about. So for today, uh, we will only focus on the content of the week one, which was asymptotic analysis. Okay, so um, yeah, so I'll the way we'll proceed is I'll not assume that you have watched the lectures. Of course you should, but I'll just try to give a quick summary or a recap whenever you come across questions of that kind. So uh, yeah, so that you don't miss out. Okay, there's a request to change the time for tutorial to 7 to 9. Okay, so um, can we okay, is everybody fine with 7 to 9, or is there an objection? Okay, somebody is not okay, then yeah. um, okay, somebody has raised a hand. uh, you have a question? uh,
No, ma'am, I'm just okay with the time. Yeah.
oh, okay. So there are some that are okay and some that are not okay, so um, okay, Saturday same time. Is Saturday same time fine with all? Um, okay, so maybe what I'll do is I'll create some poll and I'll give you the options. So I'll create a poll on Swayam on the same portal. So we'll go with the majority. Is that fine? Okay, a lot of people prefer Saturday. Okay. Okay, yeses and nos. Okay. So okay, so I think the best way to proceed is that maybe we'll create a poll, and you can vote your preferences, and yeah, and then we'll go with the majority decision. Okay. Um, does that sound fine? Okay. So I'll do that today right after the tutorial. I'll set up a poll. Um, and yeah, I'll so there is a drive that I'll create where so all these lectures are recorded. Even now this lecture is being recorded, and we'll have a recording of these sessions, and I'll post it on YouTube, so you can access it from there if you're not able to attend. And even the notes for the lectures will also be shared. So in the same drive, maybe I'll try to put the poll. Okay. So okay. Are there any other questions regarding the logistics? Okay, okay. So generally we'll have a 2 hour session, but today is the first session. So I'm imagining it will maybe like go for 1.5 hours. So it will be a shorter session for today, but yeah, let's see. Okay. So the topic for the first week is what is called asymptotic analysis, and yeah, and so just to give a quick recap, what this is let's say let's say you have Alice, and I mean I have some problem P, and I tell you write a program for solving the problem, and Alice quickly comes up with an algorithm. She has her algorithm, she runs it, and then we have Bob, and Bob also writes his own algorithm um, on his own machine, and he runs it. Now I want to check whether the algorithms that these people have written, are they indeed correct. So what I'll do is I'll give them inputs, and I'll ask them for the output. So maybe my input is I1, and the output of Alice is O1, the output of Bob is O2. But it so happens that Alice's machine answers for this particular input very quickly. So she answers in like say 5 seconds. but Bob's machine is taking a long time. So Bob maybe say answers in some 20 seconds. Now it looks like Bob's algorithm is faster. It looks like Alice's algorithm is faster, right? So what I do is I give the second input and I ask both of them to run. So now it so happens that Bob's answer comes first. So Bob say answers in say 3 seconds, but this time Alice takes longer time. So how do I know which algorithm is better in terms of running time? So right now the only thing that I care about is the running time. I don't care how much space they are using. Assume I have a lot of space. So the resource that I really care about is only time. And what's happening is on different inputs, both are taking different times. Sometimes Alice is faster, sometimes Bob's is faster. So I really want to know which is better for me. So yeah, so in general, this is a problem that we come across. You want to judge how fast one's algorithm is. So to settle that debate, we come up with a notion of asymptotics. So what is asymptotic analysis? It says that yeah, it says that, let's say on this side I have input, and on this side I have time. And yeah, and what's happening is that we're going to plot the time taken on a particular input length along this grid. So let's say we plot Alice's first, and it goes something like this. Okay, so this is what Alice's function looks like. So f of n is Alice's function. And let me yeah, so let me plot now Bob's function. So what happens is, initially um, Bob's algorithm was taking more time. So that's what we saw, right? So maybe Alice was taking some 5 seconds, but Bob was taking 20 seconds. So initially Bob's was doing really bad, but later on it sort of stabilized. So later on it's always taking more less time than Alice. So what we do is, we don't care about small sized inputs in most of the time. We care about large inputs or the behavior towards uh, large inputs. So what we do is we say that if there exists a point where before that we don't care which was faster. So we don't care whether uh, f was faster or g was faster before this point. But what we know for sure is, beyond this point, it's always, whenever, no matter what input you look at, it's always going to be the case that f is taking more time than g. So it's the behavior that we are looking at from some offset. So let me call this offset n0. So what we say is, if there exists an n0 such that for all inputs greater than that, the value of f is always greater than or equal to the value of g, then you say that g is faster. So is that making sense, or are there questions regarding this? This is something you might have seen in the lectures already. I'm just giving a quick recall. So then what you do is, we have a notation called big O. So we call it big O, and we write it like this. Then we say that G is order f. So does this make sense, or are there any questions regarding this? Feel free to ask me before we move to the questions. Lalita has a question, is it? Okay. So So for now, let's just have one notation in mind. There are a lot of other notations, but right now we'll not talk about it. So, or maybe I'll just rewrite it. So what this really means is, g of n is bounded by c times f of n for some constant c. Okay. So that's something you might have already seen. So what we'll do is, we'll take some simple examples. Okay. Okay, so here's the first question. You have been given three functions, 2 to the n, that is f1, and f2 is n to the 3 over 2, and f3 is n log n. And what you want to do is, you want to tell which, write them in the increasing order of their asymptotic complexity. So for example, if f1 is faster, then f2 would be ordered f. So okay, there are a couple of answers. I'll wait for others also to try out. Um, okay, good. A lot of C's. Okay, so does anybody want to explain, unmute and explain, or write, explain your answer? Okay, so uh, let's break this into smaller parts. So let's look at f1, which is 2 to the n, and f2, which is n to the 3 over 2. So how do we, so according to most answers, um, we have f2 is a faster function than f1. So how do we convince this? Okay, okay, I see one answer in the chat. That is along the correct lines. So one thing that you could do is, you could plot these graphs, and you'll see that this f1 will sort of grow exponentially like that, and f2 would probably be something like this. So there would be some point beyond which it sharply takes over. And what you could do is, you can just take log on both sides. So let's say you take log of f1, so that would be n, that I assume the log base is 2, so that would be just n. And if you take log of the f2 function, then that would be 3 over 2 times log n. And you clearly know that the logarithmic growth of a function is very small than that of a linear function. So linear function would go something like this, but logarithmic would probably go something like this. So this is something you already know. So sometimes it just helps to take logs on both sides and just see, although it's clear from this example. So that's how we know that f2 um, is order f1. So is this clear? Yeah. So somebody, says you can substitute the values in the function and see that. Yeah. Okay. And so what about f2 and f3? f2 versus f3, which is n to the 3 over 2 and n log n. Okay. So so again, you can do substitutions at values, you can draw the plots and you can see what happens. You can also do the same trick again. Um, you can do log also, that would also work, but you can also just compare. So this n to the 3 over 2, we can write this as n times n to the 1 over 2, and now the fight is only between n square root of n and log n. And yeah, and yeah, clearly the log function is a lot slower, so you can even take log at this point and see that this becomes half log n, whereas this becomes log n, which is a very slowly growing function. So yeah, again, so f3 order f2. So just one comment I have is looking at the chat. So the correct way to write this is by using this notation, belongs to, or you can even say f3 is order f2, but writing this is not correct. Does anybody see why this is just a semantic issue? And yeah, I mean, I just want to point it out. There's nothing. Okay, somebody says it's confusing. um, okay, so what happens is, if I write n, so n is order n square. Is this statement making sense? N is order n square. Does everybody agree? If you agree, you can maybe react with, or if you have questions, you can type it, right? I think everybody agrees. And what about 2n? Is 2n also order n square? Yeah, so everybody agrees, right? So if you use your equality in the strict sense of equality, what this would mean is n is equal to 2n, and then you can really go absurd. You can prove 1 equals 2, 0 equals 1, and so on. So it does not make sense to write something like this. And that's why this equality is not equality in the sense that you use in mathematics. That's why, to just avoid all the confusion, we use this notation of belongs to, or you can just say f is order f2. So it's not yeah, it's not I mean, I'll not bug you for this, but I just want to let you know that this is a practice that we follow. Okay, so is the question clear, the first one, or are there any questions or comments about it? Okay, good. So we'll move on to the next question. Um, yeah, so Ravi says that order n is a set of functions. Yeah, that is perfectly correct. Okay. Um, okay, there's a question in the comment section. What maths topics are needed to understand this? So basic basic concepts like functions that we are seeing just now, maybe some basic operations, logarithms, and so on. And yeah, other than that, I don't think we assume much. um, yeah, sets, relations, uh, yeah, only the basic topics. Other than that, I don't think we assume any background. But you might need some coding. Uh, I mean familiarity, because there would be some assignments, I guess, about programming. So yeah, I think other than that we are not assuming anything. Okay. So probabilistic analysis, if that's a part of the lectures, then we will cover it. Otherwise, otherwise we will do it only if there is somebody interested. There are enough people who are interested. Then we can take it up in the tutorials. But otherwise, the syllabus for these tutorials would just be whatever we covered in that particular week. So yeah, and if you would want me to discuss some solutions from past assignments, then we can do that, but you can let me know beforehand. So yeah. Okay. Okay, so yeah. Yeah, so I already see some answers in the chat. Good. So for others who have not tried, just maybe take a couple of more minutes and try this out. So um, there are a couple of hands that are up. Lalita, Geeta, Anusha. Do you have any questions? Okay, so a lot of people in the comments saying B, which is correct. So anybody who would like to explain their answers? Substitution. Okay, good. Okay, yeah. So yeah, I think, yeah, one thing that you can of course do is you can you can start substituting. So t of n is equal to t of n minus 1 plus 1. And so how do we, so what do we write in place of how do we write t n minus 1 in terms of smaller terms? Yeah, recursive substitution. So that is t of n minus 2 plus 1 plus 1. And you can keep on doing this. So at t of n minus k, what would be the value of the function? Okay, maybe I'll write it like this. So you keep on continuing like this, and what will happen at some k? How many ones do we have? Exactly, you have k many ones, and in particular, if you take k to be n minus 1, then you get t of n is equal to t of 1 plus n minus 1, and t of 1 is 1, which is what is given to us. So this is the base case if you think of it in terms of recursion. And yeah, even if you don't know what that is fine, you don't need it for this. So this is n minus 1, and this turns out to be n, which is order n. But order n is not the only correct answer here. There are there are multiple correct answers. Can you see now? Yeah. So Ravi says CD. That is, yeah, BCD. All of them are correct. So in fact, yeah, I'll just admit the people in the queue. Okay. So like you are observing now. So in fact, T of n is order n. It's also order n square, and it's also order 2 to the n. But the best answer among all this is definitely order n, because it gives you closest function that wraps up your function. So but I just wanted to convey this point. Okay. So are there any questions regarding this? Um, okay, so Ravi has a question. In exam, what will be accepted? All okay. Yeah, if it's an MCQ type question, then then you should mark all correct answers. If it's a, I mean, descriptive type answer, then you should just give the best possible approximation that you can give, which is in this case order n. Okay, so how are all other correct? Okay, so by definition of the order notation, what we say is f is order g if f is bounded by c times g for all. Okay, I'll write it like this: if f of n is at most c times g of n, um, for all n greater than equal to n0, and for some constant c. So if n is at most some constant types n times n, then it's also at most some constant type times n square, and also some constant times 2 to the n, right? So we are just giving a worse and worse bound, and that's why it's falling into the order of all those functions. So is that making sense now? Pratima, does that clear the doubt? um, can you hear me? Okay, good. Okay, so okay, good. So okay, there's one more question from Divyam. Can C be fraction? Yeah, good question. So C need not be integer. It's just some real which is non-zero, or yeah, positive non-zero. So yeah, it can be any fraction or rational or anything that you can imagine. Okay, good. So okay, so we'll move on to the next question. This is also similar exercise. Okay, sorry. Sorry. I'll maybe address one more comment. So I think Aditya is asking why order log n is not correct. So anybody would want to answer that? You can unmute and speak. I highly encourage. Yeah, yeah. So Sri Charan, Dheeraj, yeah. I think, yeah, all of you are on the correct line. Um, so you don't write it like this, no? So this is incorrect, because n is a n is a slower growing function. So if you just substitute for some values of n, you'll realize that n is a slow growing function. So you can't write something like this, and hence n is not order log n. So I hope that addresses your question. So if not, then maybe we can talk at the end of the tutorial. I'll stay back if you have doubts. So okay, good. So maybe I'll move to the next question. So this is again the same exercise. You have a lot of functions now, and you're going to arrange them in ascending order of growth. Okay. So, yeah. Um, okay, so I think most of you have got it right. So we'll discuss this answer, but before that, there are a couple of comments that I'll address that first. So, so Yog is asking for the references. Yeah. So maybe I'll just write it here. You can take a look at it. So everything that's going to be discussed in this course um, is so Corman is a really good Corman. It's called CLRS. Um, so Corman is the first author, and then you have Liu, Reiserson, and so on. So this is if you just write Corman, I think you'll find the book. This is a pretty famous book, and um, yeah, anybody who wants to learn algorithms basics to advanced, I think Corman is like a bible for algorithms. And second reference is Kleinberg Tardosh, and both of them have really good exercises problems. If you want to if you want more problems to work on, then both the books have ample examples. And Das Gupta is also a really good book, but for this course, I think these two would be more than sufficient. But I'll just write it in case you are interested. You can take a look at Das Gupta's book. So yeah, these are the references, and you can find the copies of this online. So yeah, this should be pretty accessible. And yeah, that's all. And was there anything else that I was supposed to address? Okay. Okay. So yeah, so let's look at the answers. Okay. So maybe I'll just start with comparisons one by one. So let's compare F1 with F2. So between F1 and F2, we have 2 times n to the 1 over 2, and here you have n to the 2.5. So clearly, this is uh, this is a very slow function. So you have F2 is F1 is order F2, or maybe I'll just write it here. So F1 is smaller than F2. Now we'll take this F3 and compare it with both of them. So where does F3 go? Yeah, F3 goes between. So you have now F1, F3, F2. Now let's look at F4. F4 is 10 to the n. So where does 10 to the n go?
It has to be last.
It has to be last.
Uh, Sorry, penultimate, not last.
Yeah, amongst these, right? We are only comparing between F2 and F4 right now. So
Yeah, last.
yeah. So we have 10 to the n here because this is an exponentially growing function. And what about F5?
Last.
Last, yeah.
The last.
Yeah, good. And what about F6?
It has to be before F2 and
Mm-hmm.
after F3.
Yeah, exactly. So F6 has to be between F3 and F2 because you have n square log n. So clearly this exponent is more than the exponent here. So F6 is slower function than F3, and between F2 and F6, the you have this n square as common terms, but then the competition is between square root of n here and log n here, and we already saw that log n is a slow growing function. So
Ma'am, it creates real confusion when you say slow function. People start thinking that the algorithm is slow, but slow function means the algorithm is
okay,
faster.
okay, yeah, good, yeah, maybe I'll just stick to order. I'll just stick to order then. That F6 is order F2. So yeah, I think yeah, all of you got this right. And one thing that's again regarding the notation is some of you are writing in the comments that I mean F1 is, so maybe, I mean O of F2, where this O is small. So the capital O and the small o are two entirely different notations. So this is the big O that we learned, and this is, we literally call it big O, and this is called little o. And uh, yeah, and the difference so have you done this in the lectures, or does anybody know the difference between the two notations?
In capital O, the quality is included, but in small o, it is strictly greater.
Exactly. So here you have some constant c such that Fn is at most c times g of n, but here you have a strict inequality. uh, yeah, so that changes the meaning. So for example, n is um, okay, maybe I'll maybe not get there for now, but yeah, just to yeah, just to make a point, these are different notations, so be careful when you write capital or small o. And yeah, maybe if there is time we can do examples of this time of these types. And yeah, I think that's all for now. So are there any questions regarding this, or anything that we saw so far? Okay, yeah, there's a comment which says by Divyam, which says if we substitute, then we need to check for big values only. So yeah, so that's the point of the whole analysis, that you don't know what big N to check, right? What if you check for 10, for 1000, and at that point you have F1 is greater than F2, the value of F1 is greater than F2. But let's say you check for uh, 1 million, and there you have something different, and then you just keep on going higher, and I mean you don't know what point to look at. So that's not a very robust way, right? So you can't just evaluate at some point and then say that whether the function is um, I mean you can't compare like that. So one way would be that you actually plot it, but that's something you can't always do. So one way is something that we are doing right now. So we are mathematically looking at functions, sometimes taking logarithms and tricks like that. So I mean, is that making sense? um, Divyam, okay. Does it mean for most of the cases, as in?
If for most of the cases f1 is greater than f2 is greater than f1, then we have to consider f2 is means f1 is order of f2. That I meant.
It's not most of the cases. It's that beyond some point, it's always going to be that f1 is greater than f2. Only then you say that the function is bigger. Um, so maybe there is lot of variations happening, but after a point, you are sure that one function is always taking larger values than the other. So, for example, if you look at if you just look at n and n to the 2.5, you are sure, right, that beyond in fact here it's easy, because if you just take 1 or 2 from that point itself, n to the 2.5 starts taking larger values, and it will always take larger and larger values. So
Yes, no,
uh,
after some point every case is greater, like that.
exactly, yeah. Okay, good. Okay, so if there are further questions regarding this, maybe we can take it at the end of. I mean, once we are done with all the questions, maybe those who have doubts can stay back. We can repeat this question for those who want it to be repeated. Okay. So, okay, good. So, I mean, yeah. So other than that, like other than repeating the question, are there any other doubts in?
Ma'am, will master's method will be covered in this?
Um, okay, in the lectures, I did not see that. I did not see that in at least in the week one content. I'm not sure if it's in the week two content, but mm, yeah, if it's out of syllabus and if we want to do it in the tutorial, then explicitly please let me know that you would want it to be covered. Only then we will do it. Um,
Ma'am, if time permits, please have it on the.
Okay, okay. Yeah, so um, yeah, okay. So in general, throughout the course, if you have any topics that you would like to be covered in the tutorial, you can mail me or you can use the Swayam portal and just let me know beforehand. We will cover it. So maybe next week we will do one at least one example of master theorem. Okay.
Ma'am, N to the power 2.5 is F1, but we wrote it as F2, ma'am.
Uh, oh yeah. Sorry. Yeah. Thanks. So this is F2 and this is F1. Thanks. Okay. Uh, again, I think. Sorry. Okay. Thank you. Okay. So we'll move on to the next question. Um, okay. Yeah. So here you are given some statements um, regarding the order notation, and you wanted some of them are true, some of them may be false. So if it is true, then you need to give a proof, and if it is false, then give a counter example. Okay. So let's do this one by one. So do you think one is true? How many?
Oh, ma'am, log of negative. Do we take log of negative?
In this case, we don't need it, right? At least in this case, we are only doing.
Um,
Hmm?
if the function is decreasing, then we can take negative of that.
Uh, you mean something like 1 over n, a function like 1 over n. Is that what you meant? You meant the function being decreasing, right?
Yes, ma'am.
Uh, yeah, so log of 1 over n is well defined, no? Does that make sense?
Ma'am, I was just thinking that if Fn is somehow less than Gn, but log of Gn is less than log of Fn. Is it possible? That's where I'm getting confused a bit.
Okay, okay.
I'm trying to search for that function.
Okay, so okay, maybe we'll discuss the answers first. Then, yeah, then we can talk about. I get your question. Okay, so the first question, I think, yeah, I think mostly everybody thinks that is true. So let's write what we have. We know Fn is order Gn, and what that means is that there is a C such that for all n greater than equal to n0, and there's an n0, such that f of n can be bounded by this constant times g of n. Now if we take log on both the sides, then you have log 2 of fn is at most log of c times dn. And how do we split this further? So how do we write this, expand this further?
I'm not getting what you're trying to say.
So this step is fine.
We can use the log formula, log 2c plus log 2gn.
Exactly. So this is same as log
The
2.
RHS. You meant to say that you wanted to expand the RHS.
Yeah, yeah, yeah,
Okay.
yeah. Yeah. So yeah, and this we can always write this as some other constant times log 2 of gn, right? So is all the I mean, is every step fine for all, or is there any confusion? Or we don't even need this actually. In fact, this is just a constant, right? So this is just some constant. So beyond this point, it's always that log of fn is bounded by the log of gn. So we can conclude that log 2 of fn is order log 2 of gn. Is this fine with everyone? Okay. So there are some hands that are up in the queue. If you have questions, then yeah, this is a good time to ask. Um, okay. So okay. Okay, so just to address the comment that Ravi had, so at least in the steps that we saw so far, you don't really need, um, I mean, the negative and so on part, right? So at least do you agree on that?
Ma'am, this derivation is fine, ma'am, but I was thinking
Yeah,
otherwise.
yeah, yeah, yeah. Sure, sure. Yeah, we can talk about it later. So okay. So what about B? How many think B is true? And if not, then you can write your counter example in the chat. Okay, true, true. Okay, so let's take a look at this. So you have um, 2 to the fn, and this is 2 to the um, I mean okay, and you can always write this as 2 to the gn to the c. So yeah, Pratima says false, and yeah, I vote for false. So do you see now after this? So first of all, are the two steps clear? What we did is just math identities. So if that is clear, do you see now why this should be false?
Ma'am, can you repeat?
Yeah. So first question is, are these two steps clear?
No, ma'am.
Okay. So what we did is we simply plugged and placed the definition um, of the order notation. We know that f is order gn, so it's bounded by some constant times gn. So that's what we did here, and this is uh, this is your law of exponents, that if you have uh, a to the b to the c, then that's same as a to the b times c. So that's something some basic identities that you must have seen already. So that's the only thing that we did so far. So is this fine with everyone? um,
Yes, ma'am.
okay, good. So the question is, do you now see why this is not same as order uh, yeah, this is not same as order 2 to the g of n. In the first case, it was true that if you take log, you have that f is order gn. Now if you take log, it's still preserving, but um, yeah, but in this case, that's not happening. So do you see why this is not true based on the identity that we just wrote?
Excuse me.
Mm-hmm.
Ma'am, like I was just thinking of another way of solving this.
Okay.
Like if we take just a log on both the sides without comparing it, like a 2 fn. So like it would be 2 into log of fn and then 2 into like log of g of n, right?
Hmm.
So like according to that, like when log f of n is like bigger of log of g of n. So like one like if we just multiply the same constant both the sides, it should be 2, right?
Yeah.
That's what
So
I.
yeah, so that's a good point. So the thing is, when you take so it only works in one direction. So let's say you have you're comparing n and 2 to the n. These are the functions you are comparing. Now if you take log, you get log n here, and you get n here. Okay, and now you know that this function is greater, and you conclude that this function is greater. But that's not always going to happen. So for example, you let's say take n and you take n square. You want to compare these. Now you take a log, and what you get here is log n, and you get here 2 log n. Okay, so log n is in order 2 log n, right? But this is not true. So is that making sense? Are the two examples fine, or are there any questions about
Okay, ma'am, like I got about the example that you gave, but like I didn't really understand how it's connected to the like what I do.
yeah, so what happens is log you that's what you did, right? You took logarithms on both the sides, um, and then you compared their
Okay, 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 yes,
huh,
yes,
huh.
good,
So
yeah,
what I'm
good.
saying is, as long as the two functions are like very far apart, like exponentially, when one function is exponentially larger than the other, the logarithm thing, the log scale will preserve the hardness. I mean the inequality, let's say. But when the two functions are not very far, they're not very far from each other, they're comparable, let's say, they're not like exponentially large, then what happens is, even when you take the logarithm, it's not going to preserve that inequality. So
Okay, ma'am.
although
So like after some point it might be false, which
yeah,
I did.
yeah, so if log tells you that one function is smaller than the other, then you can always conclude that their I mean You take their exponents and you, this is a valid conclusion. But if log tells you that no, two functions are comparable, then you can't necessarily lift that answer. So
Okay, okay, yes.
it's only one direction.
Okay, yes. Thank you.
Okay, good. But that's a natural and a nice thing to try. So yeah, so that's the same reason why we are saying this. So here you have, let's say, n and n square. So think of c as square. So n and n square, you know, the n square is asymptotically, uh, I mean, n is order n square. So for the, okay, sorry, what am did I,
Hello.
hello.
Here you wrote like n is not a big O of n square.
Sorry. Yeah. I think yeah. Uh, okay, so this is maybe not a good example. Maybe I should have compared a smaller and, yeah. Sorry, I think I did
Yes.
in the wrong. Yeah. Maybe
Yeah.
let me
So
take.
so I think it works because if 2 to the power g of n is less than 1, then
Hmm.
raising it to a power c will be smaller than 2 to the fn. So
Hmm.
it is a counter example can show it.
Yeah. Yeah. Exactly. So the c that we are working with is a fractional. I mean, is something less than one. So.
No, not c. 2 to the power gn is less than 1. So if fn is bounded by gn and
Mm-hmm.
gn's range is between 0 and 1, suppose, but it is an upper bound for fn. So 2 to the power gn will be a rational number, a fraction, 0 and 1,
Mm-hmm.
between 0 and 1, and raised to c will be smaller.
Hmm.
So it's not always true. So by counter example, this is false.
Yeah, the counter example that you are working with is restricting the G's domain, I
Yes,
mean
yes,
G's range. But
yeah.
yeah, that is correct. But what I'm saying now is, if C is less than one, then also this is another counter example, because I mean, for the same thing that we tried just now, instead of C being 2, if you think of C as half, then uh, yeah, then logarithmically you have that, um, I mean I mean, they are comparable, but here that's not. So I mean, does
Okay,
that,
okay. Yeah, yeah,
yeah.
understood.
Yeah.
I understood.
Yeah. So again, same thing happens here. If C were fractional, then this could be a very small function.
But ma'am, the relation is already given. No? Fn belongs to uh, big O of Gn.
Yeah,
So
Fn
even
belongs
if,
to big O of Gn, and that's why you, sorry. Yeah, and that's why you have this, right? That's where we use the definition. But the fact
yeah,
that this is in the exponent means that
correct,
C can be taken out of the whole equation.
correct.
And if C is like fractionally small, I mean, is like a small fraction, then this could become a very small function. Like, this is happening because we are dealing at exponent. So you can think of this as uh, C being half, like in this n and n to the 1 over 2
Mm-hmm.
example.
Yeah, getting your point. Don't we have any bounds on C? I mean, whether it should be greater than one
Yeah,
or it can take any value.
it can take any value greater than 0, real value.
Okay, and the problem is when it takes value between 0 and 1.
Yeah, exactly. So if C were greater than 1, then this shouldn't be a problem. But uh, yeah, the problem actually happens in the range 0 to 1. Okay, so is this clear to everyone, or are there further questions? Okay, good. So what about the third part? Mostly I saw, yeah, false is answers. Okay. So in that case, do you have a counter example?
We take Fn as log of n, Gn of as n, G of n as n. Then log of n the whole square is always less than n. Oh, that is
is
true.
same.
Sorry,
Huh.
sorry.
Yeah,
My mis-
no worries.
Oh, both taking one as n, another as 2n.
Okay, but constant.
Fn is n,
Okay,
gn
okay.
is 2n.
Let me write it. Okay. Mm, yeah. So you're saying Fn is n and Gn
Gn is
is
2n.
2n. So f square would be n square and f
It's
square is
not.
not order Gn. Yeah, that is correct. So in fact, you can even think of you can think of this as having fractional part. So maybe another example could be that fn is maybe gn is n square, but fn is something that's like 1.5. So f is still order gn, but when you square it, f square becomes n cube, and now n cube is no longer uh, uh, cannot be bounded by n square any longer. So f square is not order gn. So in fact here you can take anything more than um, more than 1, anything. So you can replace this with n to the 1 plus epsilon for any epsilon greater than 0, and it would still work. So is this are the both counter examples fine? Yeah, so in particular, I guess if you take epsilon to be 0, then I think what we get is your is the example that Ravi had shared. So okay, so are all the three parts clear? So yeah, there is another counter example by Patwari, which is also correct. You can take f as n square, g as n cube, and you get f square as n to the 4. Okay, good. So yeah, so are there any questions? Okay, so we'll move on to the next question. So okay, what's the time? Okay, so here is another question. So what you have is you have an array of numbers. So you have an array that has n integers, let's say. So this is I mean, I'll not worry about the pragmatics of the program. I'll just index my array by starting from 1. So this is a1, a2, and all the way up to an. So you have n integers here. Okay. And what you want to do is you want to create a two-dimensional array out of this. So what we want to create is a two-dimensional array, uh, n cross n, where I'll maybe index the rows by I. So let's say I is from i's, and here you have j's all the way up to n, and all the way up to n. And yeah, so what we do is whenever the value of I is strictly less than j, so okay, I'll maybe think of this as an upper triangular matrix. So whenever the value of I is, so for example 2 here is more than the value at the column, I don't care what you put here, you can write anything, but whenever I is strictly smaller than j, that is, say for example this, here the I value is 1 and the j value is 2. So for these all these entries here, what I want to output is I want it to store the value of the sum of maybe I'll just write it. So here maybe I want a1 plus a2, and yeah, so here I want a1 plus a2 plus a3. Okay, so basically you look at the I value, you look at the j value and add up all the entries. So if your I is here and j is here, then you add all the entries from here to here and write into the matrix. So that's the simple question, and maybe you can read it again, and it does not matter to the left what happens. So you can write you can write anything, it does not matter. So here is one algorithm that someone has written which does the job. So okay, sure, yeah, no worries. So this will be yeah, this will be recorded and uploaded in the YouTube. You can check it out later. Okay, thank you. So if you have any commitments, feel free to leave. Yeah, that's not an issue. Okay, and so for those of you who are staying, yeah, so here you have a very naive, very simple algorithm that does the job. So maybe just take a look at it, and the question that we are going to ask is, what is the running time in terms of order notation for this algorithm? Okay, okay, good. So there are two answers, one is n square and one is n cube, I mean order n square and order n cube. One of these is correct. So yeah, so you can, for the rest of people, I'm just giving a small hint that one of them is correct, so you can try this out. mm. Okay, so the hint is that exactly one of the two answers is correct. So if n square were correct, n cube would also be correct by the previous examples that you saw, right? If something is order n square, it's also order n cube. So what? So yeah. So what is that?
Um, is the third line also an loop? Like add up array
Yeah,
entries?
so the exactly good, so that's the point where yeah, where it's gonna take up more time, because what this algorithm is doing is it's just going through ai uh, ai all the way up to age, and it's just going to add it very naively, it's not doing anything smart. So that was the catch. uh, Good. So now that it's clear, hopefully, so uh, yeah, so what do you think is
Basically, I assume that third line is a simple operation. It's not a for loop like thing. That's why I'm saying it's order of n square.
yeah, but for values of I and j that are very extreme, it is actually going to end up doing all the way, like a1 plus a2 plus a3 and all the way up to an. So it's not something that could just, I mean, it's not like order one type operation. It's something that it's
But
taking.
it's still not mentioning it explicitly. That's why. I mean, even in question, it's not being mentioned.
Mm, well, I mean, how else would you add those entries if? Okay, maybe. I mean, it just means what is literally written there. It just naively uh, adds up. So, okay, that's what the question is supposed to be. So given that, what is your answer? NQ, right? So most of the answers are NQ. But if I want to, like someone may say that like in some operations it's not really adding up everything, so maybe it's not really taking that much time. So if you want to mathematically do it, then what you'll do is, um, you count the number of operations it takes in every step. So for example, yeah, so that's the point. Maybe I'll just say this again. So what is happening here is, I'm not really saying that this is a loop, but what we are saying is it is naively going to take look at that ith entry, and it's going to add it to the next and next and next until it goes to aj. So we're not saying this is a loop, but uh, the question is, uh, is that going to add up to the complexity? Is it still going to be n square because of the two loops and not going to add anything, or is that actually going to affect? That's the question. So it's not about like whether the loop being there or not. The question is rather, is it adding to the complexity, which is what we would mathematically like to prove. So
I
is
mean, if I look it as a, I mean, even now I'm not convinced that it'll take another loop. Still feels that AJ is getting added because of that for second for loop. I'm
yeah,
not still
yeah,
convinced.
yeah. So intuitively, just looking at it, just looking at the algorithm, it's not clear that it's going to add more time to it. So that's why what we will do is, we'll step by step figure out how much time it is exactly going to take. So and then we will calculate whether it comes to n square or n cube. Okay. So to just to start, like, okay, so let me just not worry about the diagonals right now. The diagonals I really don't care. So we have i's here and the columns as j's. And so what is the value that we're going to write at this, what are the array operations that are going to happen at this point?
Addition.
Yeah, addition of what? A1, uh,
E2.
a1 plus a2. And what is going to happen at, let's say, this point?
A1 plus A, sorry, A2 plus A3.
A2 plus a3. And what about here?
A1 plus A2.
A1 plus A2 plus A3.
Yeah, a1 plus a2 plus a3. And what about the last entry here?
A1 plus A2 plus up to AN.
A1 plus a2 plus all the way up to an. And for
This will form an AP.
yeah, sorry, okay, there are, yeah, if you want, I mean, if you have some commitments and you want to leave, it's not an issue. We will be uploading this recording on YouTube, okay? So feel free to leave, okay? I mean, in case you have commitments, okay? Yeah. So yeah, and what about this? Just a few entries.
A2
You
plus
start from A2 to AN.
Yeah, all the way to an. And maybe the second last entry here,
AN minus 1 plus AN.
an minus 1 plus an. Okay. So Yeah. So, I mean, you all agree? Do you all agree with me that the entire time that this algorithm is going to spend is only in all these all these queries that it makes? I mean, that is all it is doing, right? It looks at I equals 1, then j equals 1, and then it writes all the value, I mean, does all these array operations in the rows and updates the value. Then it looks at I equals 2, and then goes on doing uh, all of this. I mean, do you agree with me when I say that all that the algorithm is going to do is look at all these values, and I'm not even counting these, because I mean these are symmetric, right? I mean, whatever you do here, it's going to repeat the same number of operations here, so I'm not even counting that. Is that making sense?
Yes.
Okay, so all we have to do now is we want to count this, how many operations we are doing, right? So what does that turn out to be? So
First, in the first row, we'll do n minus 1 operations
mm-hmm.
because we have n values. Then n minus 2, then n minus 3, till 1.
Is it just n minus 1? Because here you are doing, just for this entry you are doing n.
बेटे 1 plus 2 plus
Ma'am,
up to n minus 1.
Exactly.
ma'am, can't we think it like that? I mean, like, let's say we have that first value. To get the second value, we're just adding the second value to the first value. We are
That
not
is,
doing anything else.
yeah,
So,
that is a smarter way of doing it. That is how you would design an algorithm if I give you to. But this is somebody who is very naive, and they have designed this algorithm. They are just brute. I mean, they're just doing the worst possible thing that they can. So it's not the best algorithm that we are analyzing. We're just analyzing the given algorithm.
then it's fine.
Okay. So yeah. So okay. So I mean, is everybody with me on this, on the final point that we said, that you're just going to count all these,
Yeah, ma'am.
right?
In
So
total, we have to perform n operations, and within those n operations, we have to perform n square operations, which gives n cube.
yeah,
Got it?
yeah. So if you like mathematically go on writing this, I mean, that's what they would expect you, if you, I mean, if somebody gives you this question in exam, then you'd be expected to write mathematically and get to the order and cube thing. So I'll just do a couple of steps here. So okay, maybe okay, maybe if it's clear to all, maybe I'll skip it for now because I have other questions to cover. So I mean, the whole point of this was that this particular algorithm, which is naive, which is very um, I mean badly written, does end up taking order and cube operations. So this, I mean, it's actually a nice exercise to count the whole thing and see what you end up with, and actually show that it's order n cube, because you'll end up getting n cube minus some terms and fractions and so on. So you can try that out, and that's the first part of the question, where you are asked to write this in terms of order or something. So the thing that we proved is this is order n cube. Now the next question that we have is um, okay, have you seen this notation? It's called omega.
Yes, ma'am.
Lower
F
now.
of n is greater than
Yeah.
equal to a into g of n.
Yeah. So um, yeah.
It
So
is to define best case, I guess. Best case.
yeah, that is correct. So if you can bound a function by say if f of n is at least c times g of n, then you say that for some c again, So, and for all n greater than equal to n0, then you say that f is omega g. So again, yeah, this is like the best case scenario, and the order thing you can think of as the worst case scenario. So can you see why this for the particular algorithm that we wrote, it's not only order n cube, but it's also omega n cube.
Actually, madam, these notations, that BIGO notations are also confusing. I had a question. Unfortunately, I joined it. But if you allow, then we can. If I don't know whether I miss it, but it needs some elaboration because, for example, for any algorithm, suppose if we write like O of n or omega of n, what does it make difference? Because anyway, algorithm, if a value found at first place, at first occurrence, then we say that O1. If I write it omega 1, then what does it make difference? So how they are differ to each other, that is not clear actually. Why simply we cannot write ON or omega in one simple notation? I mean, I can write for the base case simply ON, OO1, for worst case omega ON in general. So, I mean, why we need three notations, omega, theta, and that we go.
Okay, so okay, so I mean your question is why are these three different notations needed?
Yeah.
Okay, so um, okay, so maybe I'll answer that in a while, but I'll just let this thread finish off. So if anybody has answers to this, we'll finish it off. Then we'll take your question immediately. So anybody?
That naive algorithm,
Mm-hmm.
we cannot do anything better than that in Q because we have to use that algorithm. That's why I think it
Yeah.
has to be the best case.
Yeah,
Also.
good. Yeah, that is indeed correct. So what they're saying is you have been given this algorithm, and no matter what you do, it's always going to perform those operations. So you don't really have much choice here. So it's always going to do all these operations that we said, and if you count that number of operations, it will turn out to be order n cube. So that's the reason why it's always going to take at least those many steps. And yeah, and the next natural question would be, can you give an algorithm that does better than order n cube? So that was the third part of the question. So yeah, so I mean you basically have to come up with something that's bounded by this. So I think the answer, I think you already have an answer to that, right? So you said order n square. So if you do n square, so n square over n cube would be 0. So I think this part is fine with everybody, I hope. Yeah, so you can write an algorithm for doing so, like all of you were saying, where we counting it again and again, where we going over all those values. Instead we could just reuse the previous computation. So that's, you can try coming up with an algorithm, you can write it. So yeah, is all this fine with everyone? Are all the three parts fine with everyone, or are there any doubts other than the one I think Vimal had asked? So other than that, are there any doubts?
No, ma'am.
Okay, good. So to address yeah, to address this question, so um, in fact it so happens that there's an, I mean, all of theoretical computer science more or less is actually like sort of having a tug of war between this order notation and omega notation. So what happens is um, so if I have to give you an example, maybe let's say sorting. Okay, if I okay, maybe, yeah, let's stick to sorting for example. So if I give you an array where I have written integers arbitrarily, and I give you the array to sort. So you will come up with all sorts of algorithms. There may be so many algorithms that you can come up with, but I want to know the best algorithm that is there. I don't want to spend a lot of time or a lot of comparisons or operations or anything, right? Um, so what you'll do is you'll come up with an algorithm which say runs correctly. So let's say Ravi, for example, has come up with a sorting algorithm, and I'll do my analysis like just like we did right now. I'll do my analysis and I'll say that let's say it runs in time order 2.1, let's say. So okay, and now the problem here is I don't know if it's the best possible thing. All I can say is there is an algorithm which is guaranteed to give me a correct output in this much time, but I don't know if say if there exists an algorithm in the world at all which can say give me in this much time. Okay, so at this point I cannot say that it's omega n to the 2 point. So Ravi's algorithm is order n to the 2.1, but I cannot say that it's omega n to the 2.1. Or let me not stick to the problem. The algorithm. I'll stick to the problem. So this says that there is some sorting algorithm that runs in this much time, but what a statement like this would say is that there is no algorithm in the world which can do better than this, because what this is really saying is you're going to need at least this much time. There's no way you can escape this bound. So that's why we need these two notations. So generally what happens is I give you a problem, you come up with an algorithm. It's very easy to say that it's order sometime n square 2 to the n, whatever. This part is easy. So this is something we can come up with. Let's say tomorrow let's say Vimal comes up with a sorting algorithm which runs in like n square, let's say. Then my bar, so first of all I was here, now I'm going downward. Now I'm saying, oh look, I have a better algorithm, I can actually do in lesser time. Okay, but finding this omega, that is you're going to need at least these many n square operations. Something like this is very difficult to prove, and that's the hardest part in the whole area, like in the whole of theoretical computer science. Proving upper bounds, these are called upper bounds, by the way, and proving upper bounds is not too difficult, or it's not too easy also, but it's something you can do. But these are called lower bounds. These are very hard because you want to say that there does not exist any idea, any algorithm, any clever thing in the world that will solve this problem magically for you with this much amount of time. So typically giving this guarantee itself is hard. Then what you want to do is, let's say somebody says, let's say somebody proves to me that, oh look, sorting is say n to the 1.8. Okay, now what I want to do is I want to push this bound upward. So I want to make a better statement. I want to say that, oh, can I actually prove that you can't do in better than n to the 1.9. So the upper bounds we want to push downward, and the lower bounds we want to push upward, and finally like we want to meet, ideally the dream would be that your order matches with omega. That is, you're saying that let's say let me say 1.81. So what that would mean is somebody comes up with an algorithm that is order n to the 1.81, meaning I can do in this much time. And then tomorrow somebody proves a lower bound to me that, oh, it's not just n to the 1.81, it's omega n to the 1.81. What that means is that this is the ideal thing that we would want, that you can't do better than this and you can actually do in this much time. You have an algorithm for this. So this is something that we are always struggling for. This is a very nice thing to have, having a matching order and big O and omega. So when this happens, we just call it theta, average thing. So okay, so the whole point is that for simple algorithms, it's easy to give order and omega analysis, but it as the problem gets a little tougher, it becomes really difficult to get this bound. So that's why we need like a notation that separates the two ideas very strictly. So does that answer your question, or
Yeah, a little bit I understand what you are trying to say. I mean, yeah.
Ma'am, can I give some analogy?
yeah, please, yeah.
Okay, we can assume big O to be like our boss in our companies. He will always keep on pushing you to get the best possible result. Let's say you are going and saying that I have done some work, he'll ask you to do in much better way. So he'll keep pushing you to get the best possible result. And now consider omega.
Hmm.
Consider omega to be your professor. Now, as a student, you want to get the best result possible in an experiment, but your professor say that you cannot get anything better than this. You try whatever you can try, but it is not going to be better than this. That is what your omega is. Let's say I'll give you another simple example to understand. For sorting algorithm, the worst possible sorting algorithm can be of order anything. It can be as high as possible. There is no limit to it. That whatever verse can be, it can get whatever verse it is possible. But in the best case scenario, it cannot go below n log n in comparison based sorting, to be precise. So that omega will come into picture for that. That you know that you cannot get better than this in comparison best sorting. And big O, as you know that if you want to improve, keep on improving, you want to just get the big O number as low as possible.
Yeah, good. So yeah, that was a nice analogy. I hope that that clarifies things for everyone. So yeah. mm,
It is still, madam, we can understand, but particularly the definition of the when it goes to the mathematical part, now that functions and the way it is defined, then it is very difficult to correlate with the actual situation. I mean, the definition of big omega is like there is two constants c and n0, where cgn is a like for value greater than n0, it is always greater than n. So we are unable to understand, though we mug up that definition, but we cannot correlate to the actual situation. I mean, that mathematical definition, how it's applicable to a practical situation, that is something very difficult to understand. So I don't know whether it's matter or not. We should keep it all together, that mathematical part, and only we should consider the practical thing what we understand.
no, I mean you need both. So yeah, I think in the beginning of the session we saw some intuition for like why do we actually write that mathematical thing. So I don't know if that would answer your question, but we are uploading this recording in on YouTube, so you can maybe check out the beginning part of it. If that makes sense, it's fine. Otherwise, we can take it up sometime again. But the only reason why we defined it that way is that that's something that we discussed in the beginning, that like, it so happens that there are two algorithms that two people come up with, and now we want to compare. So that is something very very natural to ask, right? Because I want the best algorithm, so I want to compare them. So how do we compare? Because it may happen that on some input one is running faster, on some other input the other is running faster. So how do we break the tie? And the number of inputs is infinite, so we can't like check through all of them and see majority or something. Generally. So that's why we we say that okay, we care about large inputs, we don't care about on smaller input, small sized input, how does the function behave, but we are looking at the behavior of the function uh, towards the end, like as the input size grows larger and larger. So I mean that's the only, I think that's how they came up with this notation. I mean that's probably what their idea was, that you just want to approximate the behavior towards the end rather than looking at the whole of the function. So yeah, and the reason being that we are typically interested in large inputs. So um, yeah, but um, I mean that's something, that's just a mathematical guarantee that you have, but it's also possible that the constant that we are hiding is like really bad. So if you know, for those of you who are aware, those who can relate to, it's fine. But for those who don't know, that's also totally fine. So there are these sorting algorithms like selection sort, quick sort, right? And insertion sort. If you have heard of them. So insertion sort has quadratic number of comparisons, whereas if you look at merge sort or quick sort, it takes n log n. So you would expect that n log n is asymptotically, I mean n log n is order n square, so you would expect that merge sort and quick sort are faster, so we'll run these algorithms, right? But what happens in industries is that we don't run merge sort and quick sort for the sortings, we actually run the selection sort. Although asymptotically it's order n square is bad, but why we do that is for smaller values of n. By smaller we mean like maybe bounded by 10,000 or 10 to the maybe 10 to the 6 or something. For those values, selection sort works better than merge sort and insertion sort. So if you're only dealing with those small values of n, then it makes sense to run your selection sort algorithm. So it's just that mathematically we want to bound it, we want to have these guarantees, that's why we do all this business. But practically things may not really like follow along those lines.
And madam, one important question which I also put in chat box also. For the quiz one, the questions are completely out of the syllabus. So will it be the case for all assignment? Because I am worried that in exam something will come that I am not prepared for it. Because if you see the quiz questions, they are not correlating with the week one syllabus.
Is it okay?
Quiz one all questions, because by studying that week one material, I don't think we can answer those assignment questions.
Ma'am,
Yeah, please go ahead.
yeah, I think discrete mathematics is a prerequisite for this course, I think. Because I have a background in pure mathematics, real analysis, group theory. So I am finding these mathematical topics easy, but some of us are not finding it easy. Yeah, I think discrete mathematics is a prerequisite for this course.
Okay, so
But I think it has not written. Maybe I mean what this can be inferred. Yeah, but in explicitly it is. I don't think it is written somewhere in the course.
I don't think there is a prerequisite that is mentioned, but yeah, I mean I'll just try, yeah, keeping your thing in mind, I'll try to um, yeah, I'll try to like revise the concepts from discrete maths if and when they are needed. I didn't have that in mind. And quiz thing, so how many people relate to it, that it's not from the weeks, I mean the material, but something else? So do others also find it out of syllabus or something? Okay, okay, so okay, there are a couple of, or other people who disagree with that. If,
For me, it's just a bit hard, but it's still doable.
okay, so
Ma'am, till now, whatever we have discussed, it's the same thing in the quiz.
I designed the questions for the tutorial looking at the quiz, so that it will help you solve the quiz. So the questions and the questions and material is something that's out of my hand, so it's something that they deal with, and my job is just to, I'm not the one setting, and I don't have access to those people also, but I can try to forward this feedback
I
to them.
thought, sir, I thought, madam, that Madhav sir will be there in this session, but I was thinking like that Madhav sir himself will attend this session. And madam, we the because like the treatment of subject, he is IITian and we are not IITian, so it's a simple readout like a lecture. So we are expecting that something liquidized to that level that everybody can understand. It is a very high level IIT type of lecture, and not everybody is IITian.
Uh,
I get, yeah. So Suyog has something
yeah,
to
I mean you can search on YouTube MIT Introduction to Algorithms. So they explain it, and there's a problem session also after every two videos. I think that will be helpful for this course. Introduction to Algorithms. There's one more course, Design and Analysis from MIT, that is a bit advanced. Introduction to Algorithms from MIT on YouTube.
Yeah, great that you said it, and we'll definitely try it. But I mean, madam, still we have to go for two courses, not then parallel, because if one course is like this only, then it is good for us.
yeah. So yeah, I agree, I understand. um, yeah, but I mean the lecture material and quizzes is something that I don't design. So but the tutorials I'll try to keep very I mean starting from fundamentals, I'll try to keep it that way. um, yeah. Yeah, and in general the format of NPTEL is like that. There'll be instructors, and they'll be setting the whole material, and the tutorials run like disjointly, so we have no no connection so far, whatsoever. And yeah, so I'll just keep your feedback in mind, and I'll try to keep the tutorials that way.
You are asking hard question, that is good, madam, but then you teach us like that level, na? And we also want to learn. It is not that we don't want to learn.
Yeah, sure. But yeah, could you follow the tutorial, today's tutorial?
Sorry, madam, I joined late, so maybe I will, but recording will be available. Then I will go through it again.
Yeah, sure. Yeah. So what about others? Like, how is the difficulty of the tutorial? It's Was it followable, or um,
Excuse me, ma'am.
yeah, sure, yeah.
Ma'am, like I had a small doubt. Ma'am, like in the question of the array, ma'am, like where you told that like in an in the exam, like we had to like write it step by step. So like if you could, like maybe for one question, what would be the steps required, ma'am? Or else, ma'am, like if you have any material where there are steps,
Yeah.
so that it will be useful, like at least for one question, so then it will be easy for
Yeah,
others.
yeah. So what I'll do is, when I upload these notes, I'll write the solution. I'll add one more page after that part. I'll write the solution entirely, so you can look at it.
Okay, yes, I'm sure. Ma'am, like at least like for one question, it's like ma'am from my side, so that it will be easier to solve it. Like we'll get to know
Yeah,
what are the steps.
yeah. Sure. Thanks. Yeah. So yeah, we had few more questions, but it's okay. We can cover it next time, or you can try it on your own. So that is fine. So we have almost reached 8. So I'll stop the tutorial for today. And yeah, so I've shared my email ID with you, and yeah, I'll be reading it. If you have any doubts, or if you have suggestions on what we should cover in the tutorial, then I'll keep that in mind while preparing for the tutorial. So yeah, you can write to me on that. You can also reach out on the Swayam portal. That's also, anything is fine. Okay, so if there are no further questions, yeah, I think, yeah, the poll thing I'll do. Yeah, I'll set up a poll for, um, yeah, I'll try to do it today itself. But if that does not happen, let's say if that does not happen, in the worst case if that does not happen, then the next meeting, at least for the next week, will be on Friday same time, 6 p.m. to 8 p.m. at least. I mean only for the next week, if there is no poll that happens. Okay, so
Ma'am, will descriptive questions be asked in exam?
in the you mean the final exam that you have to write at the centers?
Yes, ma'am.
Yeah, as far as I know, I think there would be. Yeah, that's up to the best of my knowledge, but I'll confirm with them and I'll let you know. I'll confirm by next week's tutorial.
Ma'am, where are you going to post this material, ma'am?
So there's a Google Drive that's been shared with you on the Swayam, so you can access it from there. Right now I've not uploaded anything, and probably that's why you can't see, but once I do it, I think you'll be able to access from that portal.
And that meeting recording also we will get from there.
Yeah, you can get it from there. You can also directly get it from YouTube. So um, yeah, if you just search maybe design analysis of algorithms, maybe you'll find it. But yeah, the link will be there in Swayam. So
Better, madam, you give us the link so directly we can
yeah,
access
so
this.
right now I've not created the link, so I can't do it. I'll get the link once I upload it on YouTube. So I don't have one to share right away. But I think it should be very accessible from the Swayam portal. No, yeah, again, it's not the Gmeet. So what is the question about the Gmeet link thing? Is it about the tutorial or is it about the recordings?
I
Satya, yeah.
think it's about tutorials.
Oh, okay. Yeah, so the tutorials will be on the same link throughout the end of the course. Okay. Yeah, sorry about the confusion. Okay, then. Okay, so I'll see you all next week. Um, okay, thank you all for being interactive, and that actually helps.
Thank you, ma'am.
Okay, thank you all.
Thank you, ma'am.
Thank you,
Thank you, ma'am.
thank you.